After we know the meaning of logarithms, now we are good to learn the concept of logarithmic functions. Previously, we have learned the concept of exponential functions. An exponential function is a function in the form of a to the power of x, where a is a constant base. We have a requirement for this constant base a. I hope you can still remember this. We require that a should be positive, but at the same time not equal to 1. So that this function will be a smooth curve and well-defined, and at the same time it will not be a constant function. And then in this chapter, we do a similar definition for logarithmic functions. A logarithmic function is a function in the form of this, logarithm of x with base a. And here, since this number is just the base of exponentiation, we have a same requirement for this number. Whenever we learn a new function, we are usually interested in these few things. The first thing is the graphs of this function, how the graphs should look like for this function. And then the second thing is the intercepts. That means, should this function have any x or y intercepts? If so, how many are there? And then the third thing that we will be interested in is the domain of this function. First of all, to understand how the graphs of logarithmic functions look like, one good way to understand this is through tabulation. That means we can tabulate the values of this function, and then we may take a look at how the graphs should look like. For example, for exponential functions, we can draw a table like this. Here we have input x and output y, and here y is 2 to the power x. I use 2 as the base for simplicity. Just an example. So when x is 1, then the output y will be 2 to the power 1, which is 2. And when x is 2, then y will be 2 to the power 2, which is 4. And when x is 3, then y is 2 to the power 3, then it will be 8. And when x is 4, then y will be 2 to the power 4, which is 16. And when x is 5, then y is 2 to the power 5, then it will be 32. Now for logarithmic functions, we can construct a similar table. Here y is the logarithm of x with base 2. This time, when we're going to construct this table, we may want to fix a value of y first, and then we find out the value of x. That means when y is 1, that means the logarithm of x with base 2 is 1. That means 2 to the power 1 is x. So that means x should be 2. And if logarithm of x with base 2 is 2, that means 2 to the power 2 is x. So x is 4. And when logarithm of x with base 2 is 3, that means 2 to the power 3 is x. So x should be 8. And when logarithm of x with base 2 is 4, that means 2 to the power 4 is x. That means x should be 16. And similarly, if y is 5, that means 2 to the power 5 should be x, and x should be 32, etc. Now we can observe that these two tables actually have a same set of values. If we interchange the two rows of this exponential table, then we will end up with the same table as this logarithmic table. That means if we interchange x and y in an exponential function, then we will end up with a logarithmic function. This is going to be a very important hint for us to understand the graphs of logarithmic functions. Now I'm going to show you how we can obtain a logarithmic curve from an exponential curve. We have learned that an exponential curve is something like this. And this is y equals a to the power x when a is bigger than 1. That means an exponential growth. Since we know that a logarithmic function is just a result of interchanging x and y in an exponential function, that means if I make the x-axis here to be the y-axis and the y-axis here to be the x-axis, then this curve will be a logarithmic curve. That means, okay, I'm going to do this for you. Take a look. I'm going to make the x-axis to be the y-axis and the y-axis to be the x-axis. So it goes like this. Okay, I do it again. X becomes y and y becomes x. Okay, so this graph here is actually the logarithmic function that we want to know when a is bigger than 1. And of course, since we know that the y-intercept for an exponential function is 1, then here we should know that the x-intercept of a logarithmic function should also be 1. And from this diagram, we can actually obtain a logarithmic curve when a is smaller than 1 and bigger than 0. Okay, we have already learned that if I flip the exponential curve in this way, then this curve will be an exponential curve when a is smaller than 1. So that means this is an exponential decay. And now I can do the same trick here. Here I treat this one as the x-axis and this one as the y-axis. And then in order to obtain a logarithmic curve when a is smaller than 1, I just need to make the x-axis the y-axis, and the y-axis I make this to be the x-axis. So I will do it like this one like this. Okay, I do this again. X becomes y and y becomes x. Okay, so the curve like this is the logarithmic curve when a is smaller than 1. So from this transparency, you can actually obtain all kinds of curves of exponential functions and logarithmic functions. And here, as you can see, the x-intercept or the y-intercept is always 1 here. So here for the logarithmic function when a is smaller than 1, the x-intercept is 1. And for the logarithmic function when a is bigger than 1, the x-intercept is still 1. And then for the exponential functions, the y-intercept is always 1. So I hope this transparency can help you to understand different types of curves of exponential functions and logarithmic functions. Now let's organize what we have learned. For exponential functions, we know that when a is bigger than 1, then the curve should look something like this. And the y-intercept here should be 1. And this curve is an increasing curve. That means when the value of x increases, y should increase as well. And when a is smaller than 1, then we will have the case of exponential decay. But here the y-intercept is still 1. And this is a decreasing curve. Here we know that since this curve never touches the x-axis, so we know that there is no x-intercept. And the y-intercept is always 1. And since any x can be the input value of this function, so we say that the domain is all real values or all real x. Here for logarithmic functions, we have learned that when a is bigger than 1, its curve can be obtained by this one. So it should look like this. And this curve is an increasing curve as well. And when a is smaller than 1, then we know that this logarithmic curve can be obtained by this exponential curve in this way. So the curve should look like this. And this will be a decreasing curve. Now as we can see, the x-intercept is always 1. And then for the y-intercept, as you can see, this curve will not cross this y-axis, and that means there should be no y-intercept. So as you can see, xy is reversed when we are considering exponential functions and logarithmic functions. And here for the domain, since for logarithm we only require positive x as the input value, and as you can see from this curve, if x is 0 or negative, then we cannot find any output value y here. So the domain here, we will say that this is all positive real numbers or x bigger than 0. Finally, let's take a look how the shape of this curve will change when we change the value of the base. Now the base of this logarithmic function is 2. And if we change this, let's say if I make it smaller, make this value closer to 1, then as you can see, the curve will look more like a vertical line. And when the base is 1, then you cannot see anything because this is not a well-defined function. And when it decreases further, and then as you can see, if this value is very close to 1, then it will look very like a vertical line. And if it decreases, then it will look less like a vertical line. One very important concept for logarithmic function is that if we put an exponential function and a logarithmic function together, now this exponential function and this logarithmic function, they have the same base 2. And if we put them on a same graph, then these two curves are symmetric about this axis of symmetry. And this axis of symmetry is y equals x. That means a straight line which passes through the origin with a slope 1. And these two curves, they are always symmetrical about this axis of symmetry. So even when I change the value of this base, when the value of the base is the same for these two functions, they will always be symmetrical about this y equals x straight line. So I hope this simulation can strengthen your understanding of this property of symmetry of exponential function and logarithmic function.